Hey friends, Ben again. This is a video for the differential equations class. We are looking at the setup to get to Picard's iterative method. Picard's iterative method is kind of a neat little trick. It is, however, maybe not what you will use a lot of. Okay, so the thing that's going on here is that Picard's iterative method is actually a method that is used in order to prove that there are solutions to differential equations. So we're going to see how the method works. But the thing that's going on is that if you have one of these iterative methods that satisfies certain properties, and sorry, I know I'm being super vague on that, but the properties are called Lipschitz conditions, and they require about another half an hour to explain all the things about them so that makes sense, okay? But the Picard iterative method satisfies these Lipschitz conditions as long as you've got a nice differential equation, okay? So in any case, if you have a method like this that satisfies these Lipschitz conditions, then the iterative method is going to converge to something. What? That's how a lot of math gets done, by the notion that there are solutions, and you don't really know what the solutions are, you just know that they're out there. But once you know there's a solution, you can apply some sort of a computer algorithm to try to approximate that solution. If you don't know there's a solution first, then you're just kind of like shooting in the dark. If you're super smart, maybe you shoot good, you know, pow, good shooting techs, you got the solution. But we know a solution exists because we have this Picard iterative method. I'm going to sidetrack just a little bit here, okay? We had a senior member of the department, Elwood Parker. His brother, his younger brother, retired from James Madison and came to work for us for a while. And his research had to do with something that's referred to as the Parker-Sochacki method. If you got something named after you in math, you're pretty cool, okay? But he would never refer to it as that. He would refer to it as the Picard iterative method, which is what this thing is we're going to look at. The reason he called it the Picard iterative method was that he was trying to do something applied math. He's not an applied mathematician, but you know, he was trying to do applied math. And he knew he had to use a computer. So he was trying to write a computer program to implement this Picard iterative method. And he couldn't quite figure it out. So he went to another mathematician and said, hey, I'm trying to figure this out. And the mathematician said, nobody would do that. It's crazy. It doesn't make any sense. It's super slow. It doesn't help. You should do this other thing. And Ed went back to his office and went, okay, I should do this other thing. And a couple of days later, Jim Sochacki came by and said, the thing you were doing, keep doing it. Turns out, and they have written dozens of papers about just applying this technique everybody knew about, but nobody thought was very helpful. So anyway, if you try to do a little bit of research with dynamical systems or differential equation stuff, you may run into this kind of thing. And that's a field that's interesting to look at. So, all right, let's see where we get at it. And I'm going to assume that you have a copy of the homework that has a couple of theorems stated on it and definitions and stuff. So take a look at that as we go along here. Oh, thrilling. My computer has announced that I, while recording, have to install a plugin. Great. Okay, so let's try it again. It seems to have installed the plugin. Hopefully my iPad can deal with the plugin. It can. Thrill. Yay. All right, so we're referring to the Picard iterative method, but to get there, we're going to talk about a little something else. All right. So the exponential matrix technique that I refer to here, I am going to put just this little side note here. You are solving, and back up there, you are solving equations of the form x prime equals ax. So you know how with the stuff we did before the systems, we could have a problem like that, and it turned out that the solution was going to be equal to y sub naught e to the ay. Well, as it turns out, we can do the same thing with matrices. And so what we end up doing here is getting our solution with an e to the at, then times whatever the x naught is that you got for an initial condition, right? So essentially, the tricky bit in this turns out to be, what in the hell do we mean by e to the at, right? And fortunately, when we talked about eigenvalues, eigenvectors, we know, in some cases at least, how to calculate this e to the at stuff. So our method we're doing here for solving this equation, we're going to have to go think about how to exponentiate this matrix. Well, this matrix times t. And so this is actually an example that we've seen before. The two eigenvalues are going to be 2 and -1, and the eigenvectors that go with them are going to be 1, 0 and 1, -3 respectively. That gives us our similarity matrix that we referred to as P. And all we did with that is to just list the eigenvectors in order. Now, keep in mind that your diagonal matrix down here, you're going to have to think about putting the eigenvalues in the same order that you put the eigenvectors in for this. But once we've got that P, we also need to figure out what P inverse is. And if you don't remember how to tackle that, it was that essentially you would take the 1, 1, 0, -3, augment it with the identity matrix, and then you would transform this matrix on the left-hand side into the identity matrix by your row operations. And once you got that done, it would automatically end up generating the inverse there on the other side, okay? On another hand, if you're good with numeric approximations, you could just say, hey, Colab, invert this matrix for me. And because of the fact that it's got thirds in here in this part, it's going to get some, some numerical errors. But if you see 0.3 repeating, you better know that that's 1/3. All right. Anyway, once we've got the P and the P inverse, we know that we can get this e to the at by taking P times the exponential, the e to the dt. And when you've got the e to the dt and it's just a diagonal matrix, right? All you have to do is to exponentiate the diagonal. That's it. So this matrix that we're referring to here, we can get like that. So e to the at is something we can actually calculate with stuff we already have. So once you've got that there, then you can come back over here and get your solution by just saying, I want to take e to the at and multiply it by my initial condition to -1. That's exactly like what you did for stuff that was one-dimensional, not systems. The only difference is you have to keep it straight which order to multiply things in, okay? But when we come down to it there, then you get, you have to take the e to the at that's over here and multiply it by that 2, -1. And the top is a little bit messy, but the bottom is pretty easy to do. And once you've got that bit multiplied out there, then you end up here with this function as your answer, okay? Not super hard, but I have to be honest with you. I suppressed all the hard part, right? The finding the eigenvalues, that wasn't super hard. You were solving a quadratic, and so long as the eigenvalues are nice, you can just turn to Colab and let it do that for you. The eigenvectors, that was a little bit harder. I would suggest doing that by hand, but if if you're working it out using a computer, it can work out. So once you get that, you've got the matrix here for the P, and then figuring out the inverse of it. Again, I would do it by hand, but you can also ask the computer to do it for you. And once you have those two matrices, then actually multiplying this out, unfortunately, you'll probably have to do that by hand because of the fact that doing symbolic manipulations is a little rough on a computer. I'm trying to figure out how to make it work, and I'm pretty sure it would work, but you can't just say, here, do it, and get it to work. So, all right, anyway, so using this e to the AT sort of technique, we can solve these differential equations. Now, this thing that we got here, our e to the AT, we would refer to that as a fundamental matrix for this differential equation here, right? And it has the nice property that you can just multiply it by your initial condition. All right. So getting a little bit more towards the point of being able to use the iterative method, right? So we talk about systems in part because sometimes problems show up as systems, but also because you can use this system method to make your solving of higher order equations easier. Now, my examples are going to be linear because linear examples are easy to write out and see the details of. However, this works perfectly well with something that's nonlinear. It's just harder to write out, okay? So we're going to look at a second order initial value problem here. And it's just got the y double prime minus y equals 0. Okay, that's the differential equation part of it. And then we've got our initial conditions that are written out there. Okay, so here's the trick with systems. You always let your x1 be your function, and then your x2 is its derivative. If you have a higher order than that system, then you'd have an x3 as the second derivative, and x4 is the third derivative, as many as you need, okay? But this has second order being the highest, and I can solve for that y double prime. Not really hard to do. Y double prime turns out to be equal to y, okay? So when I write my system here and take its derivative, I just take the derivative of each entry, and x1 prime is really y prime, and y prime is x2. Whereas x2 prime is really y double prime, but y double prime turns out to be equal to y, and that's x1. So that being the derivative of x1, x2, means that we can unwrap it into the matrix 0, 1, 1, 0 times the x2, x1. Now that matrix is our A. And now we'll apply the methods that we know how to do already, okay? Now, in this particular case, I didn't go try to calculate the exponential. We could totally do that, and it would work out totally fine. But I want to make the point that you can do it either way, right? So we've got our matrix there. We figure out its eigenvalues. For each eigenvalue, then we figure out the eigenvector that corresponds, and that gives us our general solution. Now, here I had not actually written down that we needed to say something about the x of 0 equals 2, 1, but I'm going to go ahead and apply it here. And I just plug in the t equals 0. And so I've got this c1 plus c2 has to be 2, and c1 minus c2 has to be 1. And then I go do a little bit of algebra on that. I didn't write that down because the page is kind of cramped here and I didn't want to use a whole second page just to do that arithmetic sort of thing. Well, algebra sort of thing. But the C1 turns out needs to be 3/2 and the C2 has to be 1/2. And if you'd like, you could go ahead and merge them together into one sort of equation there and have the 3/2 e to the t plus 1/2 e to the minus t on the top, and then on the bottom, the obvious things. But what's important to us is that the top is x1, and x1 is the y that we needed. And if you go back and do this system the way, do this second order differential equation the way we did in earlier chapters, you get the same solution. Yay! If your reaction is, well, we already knew how to solve those, why would we bother? The point is that we have a way to convert these to systems, and systems, then you only need to have a first order differential equation. All right. So we have a first order differential equation here in this portion of it. It's really dealing with x prime equals ax. And the next thing we're going to look at, the Picard iterative method, allows us to say that we have a solution. If you look at your what you've got on your sheet, there's a theorem that says that when we have a first order system like so long as the derivative with respect to x, and that gets a little complicated here because we got x1, x2, and so forth, so long as the partial derivatives are all continuous, and man, are they, because they're constant. So long as those are continuous and we've got an initial condition set up around a place that they're continuous, then we can go ahead and say that there is a solution. And that is dependent upon this Picard iterative method, okay? So the setup for said iterative method is simply that you start out with a, oh, I've numbered them wrong, darn it, okay. You start out with a phi sub 0. This is your first approximation, and you just let it be your initial condition, okay? And then for each successive approximation, you just take your initial condition plus an integral 0 to t of the f of y, and I'm going to put an s here instead of a t, ds. You got to have a dummy variable in there for this to make sense, right? So the iterative method just essentially says that that we set this up here with initial condition plus the integral of f of ys. And the notion that we actually have is that if we take the limit as n goes to infinity, if it converges, and when you get a Lipschitz condition, it will, if it converges, then the thing that we get out of this will have to satisfy this differential equation that was given to us by y prime equals f of y comma t. All right. I've not gone through all the details of that, but actually I should probably not erase that. Okay, I've not gone through all the details of that, but that is the essence of what goes on with the Picard iterative method. Now we're going to look at it with one-dimensional sort of things instead of looking at it with systems. But the beauty of it is kind of like with programming in Python when you've got casting that allows you to do things with arrays that you would normally be doing with scalars. This scales up, and the Picard iterative method can totally be used for systems. And because it can be used for systems, the fact of the convergence for first order systems gives you solutions, convergence and solutions for all orders of differential equations. All you need is continuity of the derivatives of your f. That's it. Wow. You know, that is super powerful, and it's something that we can actually do some of the work of. Okay. So for our example here, we are going to be dealing with y prime equals t squared y minus t. Oh, I wrote that elsewhere. Okay. Now, what you need to realize when you're doing this is we're going to convert it over and have s's. S is just a dummy variable, but it can get confusing. So as you're going along with this, think about that you'll have s squared times y, and y will have expressions in it. You know, I probably ought to pretty that up a little bit there. And instead of y, I should refer to the thing that we actually have here, the phi. And I made that too fat. Oh well. All right. So let's go along here with what we've got. And this is enough of a detailed calculation that I had to write it out ahead of time. So bear with me. So our first iteration, we'll just say phi sub 1. I should have said phi sub 0, but whatever. Okay. But phi sub 1 is going to be just the number 2. That's not a very good approximation for most functions, but it's a start. We get to do as many steps of approximation as we want. Okay. So then the next one, you will say the 2, and that is coming from the initial condition, not from the phi 1. And now inside here, we have to put f of the phi, the previous phi that you had, and comma s. So because that's supposed to be s squared phi minus s, we have s squared times 2 minus s, right? Then we integrate it and plug in the 0 and the t. Hey, bear in mind, when I say we integrate it, if you're looking at that and saying, why is he doing definite integrals? Why doesn't he just do it as an indefinite integral? Yeah, it totally makes sense to do, but this takes care of all the details of proof stuff here. So if you had an initial condition other than t equals 0, you would need to substitute that in as your lower limit of integration. Okay. But when we go ahead and do this process, we end up getting 2/3 t cubed minus 1/2 t squared plus 2. Now, there's a piece you need to spot here, and it's not obvious on the first step. 2 stayed. When we go to the next step, those 3 terms are going to stay, and we'll get 2 more. When we go to the next step, whatever we have left will stay, and we'll get more terms. So when we plug in here the 2, and then s squared times the thing that we just got, minus s, we have to do the integration again, and we end up with, I wrote 2/18, so you could follow how it occurred, but that's going to be 1/9. Okay, so 1/9 t to the 6th minus 1/10 t to the 5th, and then the thing we already had. So then for our fourth approximation, we have the s squared, and we put that same thing in there, and minus s, and add it to 2 after we're done, but we integrate, and I had to do some simplification because I can't do it all in my head. But once we did that, then we integrated, and now we've got like a 9th degree polynomial. Ugh. But notice that it has the thing that appeared as our third approximation and 2 more terms. Okay, so I have a finalized picture here, but let me go ahead and do this the other way as well. I hope. So let's, oh, damn it. Okay, where is Desmos? There we go. All right, so hopefully all are seeing Desmos there with this. So that is the graph that you saw. Yeah. There's the graph that you saw there. Let me turn off the later approximations. So you see that the first approximation is just a constant, and then the second approximation immediately turns things into a cubic, and then the next approximation jumps up to a 6th degree. Notice there's not much difference between the cubic and the 6th degree. And now the next one's going to be 9th degree. And notice there just isn't a lot of difference between them in close to the initial condition. All right. If you did another approximation, you'd get something that's 12th degree, and there wouldn't be a lot of difference in close. But as you get farther out there, you find that it's converging farther out and farther out as you go along. So in any case, that is the Picard iterative method. We're going to look at it for 1D stuff because the details with higher dimensions is just a lot of bookkeeping. So anyway, go ahead and try some of those, and let me know what you think. All right.